Hello students, today we'll study about Kirchhoff's rule. So Ohm's law we have studied earlier that enable us to determine the equivalent resistance of a circuit, the current flowing through a part of circuit and the potential difference between any 2 points in a circuit when it has a single source of EMF. And it can be reduced to a simple series and parallel combination of resistance. But it becomes very difficult to analyze a complicated electrical circuit using Ohm's law. So a German physicist, G.R. Kirchhoff, in 1842 put forward a set of 2 rules which provide us the techniques to analyze or handle the complicated circuit. So the first rule is called Junction rule, or Kirchhoff's first rule. So it states that the algebraic sum of the currents meeting at a junction in an electrical circuit is always 0. Or in other words, the sum of incoming currents is always equal to the sum of the outgoing currents at a junction. So here you can see I1, I2, I3, I4 and I5. These all are currents. So in this case they are meeting at O. So you can see here that I1, I2, I3 and I5, they are moving towards the junction and I4 is moving out of the junction. So from the first rule, or applying the first rule at junction O, so we find that I1 plus I2 plus I3 plus I5 is equals to I4, or we can write I1 plus I2 plus I3 plus I5 minus I4 is equals to 0, or we can write summation I equals to 0. Here the current reaching junction O, that is incoming currents, are taken as positive. That is I1, I2, I3 and I5 are taken positive, and the current leaving the junction, that is I4, is taken out negative. Thus the sum of all the currents will be 0. This rule is based on the conservation of charge and reveals the fact that charge cannot accumulate at any point in a circuit. The total charge entering a junction in a certain time is always equal to the total charge that leaves it in the same time. Next is Kirchhoff's second rule, or loop rule. So it states that algebraic sum of changes in potential around a closed loop circuit is always 0. So for applying the loop rule, we use the following sign conventions. If we traverse a closed loop, that is start from a certain point and move along the closed loop to return back to the point of start in the direction of current, the product of current and the respective resistance I are counted negative and positive if in the opposite direction. Next rule is, while traversing the loop, if we go from the negative terminal to the positive terminal through the electrolyte, the EMF of the cell will be counted as positive and negative when traversed from positive terminal to negative terminal. If we equate the sum of steps 1 and 2, we get a total of 0. Now here in this circuit we will apply loop rule using the sign conventions. to solve this circuit. So here you can see that we'll have to divide this network into two loops. First loop is A, B, M, N, A. This is first loop, and second loop will be B, C, D, M, P. Right. So what is the first loop? If we traverse a closed loop, that is start from a certain point. So here we are starting from A and move along the closed loop to return back to the point of the start. So we are returning to A in the direction of current. So we are moving along the direction of current. So the respective resistance IR is counted negative. So here you can see we are moving from A to B, then B to M, M to N, N to A. So here the respective resistance, because we are traveling along the direction of current, so respective resistances will be taken as negative. So respective resistance and its product with current is taken as negative. So minus I1 R1, this is R3, so minus I3 R3. Here it is R1 is the internal resistance of this cell, so minus I1 R1, right. And second rule says that while traveling the loop, if we go from the negative terminal to positive terminal through the electrolyte, the EMF of the cell will be counted as positive. So here we are traveling from negative to positive, so EMF is taken as positive. So from loop ABMNA we get this equation, or we can rewrite this equation as I1 R1 plus I3 R3 plus I1 small r1 is equals to epsilon 1. This is the first equation that we have received from this loop. Next is loop BCDMB. BCDMB. So here the direction of current, we are moving from B to C. The direction of current is opposite to the direction that we are traversing. So we'll take the product of current and resistances to be positive, right? So it will be plus I2 R2. This will be plus I2 small r2, and the resistance we are moving from positive to we are moving from positive to negative for potential, so this will be negative, so minus epsilon 2. And here again we can see that we are moving against the direction of the current, so it will be plus I3 R3, so it is equal to 0. So we can rewrite this equation as I2 R2 plus I2 small r2 plus I3 small r3 is I3 capital R3 is equals to epsilon 2. This is equation 2. Now we will apply the junction rule at B. Here we have junction, so we are applying junction rule at B. So I1 plus I2, this is I1 and this is I2, is equals to I3. So this is the third equation. So when we will solve these three equations, equation 1, 2 and 3 simultaneously, we can find out the values of I1, I2 and I3. These currents can then be used for finding the potential differences across the various resistances. And this second rule is also a consequence of law of conservation of energy. As we go around the loop, measuring various potential difference and return to the point of start, we find that the algebraic sum of all the potential difference, that is net potential difference, is 0. Next is a Wheatstone bridge. So it is a network of 4 resistances forming a quadrilateral. It can be used to determine the resistance of a conductor. Okay, so here you can see that P, Q, R and S, they are forming, these are 4 resistances forming a quadrilateral, A, B, C, D, right? A sensitive galvanometer is connected between B and D. A battery is connected along with key K1 between A and C terminals, okay, to send current in the circuit. Now, when key is closed, or we can say when switch is on, the value of one of the resistances, say suppose a resistance R is so adjusted that the galvanometer shows no deflection, then the points B and D will be at same potential, therefore no current will flow through BD arm. In this condition, the Wheatstone bridge is said to be balanced, and the following relation will hold true, that is P upon Q. P is the resistance, Q is also resistance, R is resistance, S is also resistance. So P upon Q is equals to R upon S. Next is condition of balance of Wheatstone bridge. This can be detected by applying Kirchhoffs rule to the closed loop A, B, D, A and B, C, D, B of the circuit. So here you can see that in the loop A, B, D, A, so we are starting from A, so it will be minus I1P plus I minus I1 into R. This current is I minus I1 on this arm is equals to 0, or you can write I1P will be equal to I minus I1 into R, right? Next, in this loop we can see that in the loop B, C, D, B, so the current, the sum of the currents, so it is minus I2 Q, and here we are traveling opposite to the direction of current, so it will be I minus I1 into S, or we can write I2Q will be equals to I minus I1 into S. So here you can see this equation. So I1P is equals to I minus I1, and the second equation is I1Q is equals to I minus I1 into S. So from these two equations we can find, after dividing equation 1 by 2, P upon Q is equals to R upon S. This is the condition for balanced Wheatstone bridge. Next is a Metre bridge or slide wire bridge. So it is a sensitive device used for determination of unknown resistance of a conductor. It works on the principle of Wheatstone bridge. So construction of this Metre bridges, it consists of a 1 meter long wire of uniform cross-sectional area made up of constant tan or magnenin. It is stretched on a wooden board. So this is a wooden board. This is a board. Between points A and C, right? A scale is also fixed. This is a scale on the board parallel to this wire. This is the wire. This is the wire. And this is scale, right? The ends of wire are soldered to to a L-shaped copper strip with binding terminals provided at their ends. So here we have copper strips. Then another copper strip with 3 binding terminals is fixed between the 2 strips. between these two strips. This is another strip. The unknown resistance X is connected between terminals A and B, and the resistance box R is connected between C and D. A galvanometer G is connected to terminal B at one end and to a jockey, this is a jockey, J at the other end. Okay, a battery is connected between A and C. This is the battery with a key K, right? So working. So when this key is switched on, or when we plug in the key and take out some resistance from this resistance box, and the jockey is then slided over this wire AC till the galvanometer, this galvanometer shows no deflection, right? So that is the null point. In this case, the null point is obtained. Let the jockey touches the wire at D. This is the point, right? And in this situation, this length AD is equals to L. So what it will be? 100 minus L. So AD is L and DC is 100 minus L. So comparing it with a Wheatstone bridge, the circuit, when the galvanometer shows no deflection, so what was the condition? P upon Q is equals to R upon S. So for meter bridge circuit, X upon R is equals to L upon 100 minus L. So we can find out the value of X as X is equals to R into L upon 100 minus L. Next is potentiometer. So it is also a sensitive device used for measuring the EMF of a source without drawing any current from the source. It is also used for the determination of internal resistance of a cell and comparing the EMFs of two cells. So the principle of a potentiometer is that when a steady current is passed through a conductor of uniform cross-sectional area, the potential drop between 2 points on the wire is directly proportional to the length of the wire between these points. So this is the principle. Now in this diagram you can see, consider a source. This is the source of EMF epsilon is connected across the ends of a uniform wire AC. So let the current that flows through the circuit be I. Okay, then the potential difference, or the potential drop across the length AB of the wire will be given by V is equals to I into RAB. RAB is the resistance of length AB of the wire of cross-sectional area A. So RAB will be equals to rho L upon A. So the potential drop V will be equals to I into rho into L upon A. So this potential drop V will be proportional to L. Therefore the potential gradient V upon L is constant. Next is the construction of potentiometer. A potentiometer consists of a long 4 to 12 meter uniform wire made of constant 10 or magnenin. So here we have four wires stretched in parallel lengths having 1 meter each between two fixed binding terminals on a wooden board. A graduated scale is also fixed on the board parallel to the wire. Here you can see this is a scale. A standard cell, this is a standard cell, along with a meter, a key and a rheostat is connected across the binding terminals to allow a steady current to flow through the potentiometer wire. This will cause a constant potential gradient along the length of the wire. Now some of the applications of potentiometer are, we can determine the EMF of a cell. So for this a standard battery, here you can see we are using the same diagram. A standard battery E is connected across the ends A and B of the potentiometer wire along with an ammeter, key and a rheostat. This arrangement maintains a steady current through the potentiometer wire. The positive terminal of the cell whose EMF epsilon is to be determined is connected to the positive terminal this is the cell and its positive terminal is connected to positive terminal of the battery, and the negative terminal of the cell is connected to a jockey. The negative terminal of the cell is connected to a jockey through a galvanometer G. This jockey J can also be slided over the length of the wire. Next is the working. So when key K is closed, by inserting the plug in the gap, a steady current I starts flowing through the potentiometer wire. Then what happens? The potentiometer wire creates a constant potential gradient along the length of the wire. Now when we start sliding the jockey from A over the wire AB till a point J is reached, for which there is no deflection in the galvanometer, this is called the null point or the balance point. In this position, the EMF of the cell is equal to the potential drop across the length AJ of wire. So epsilon is equals to I R AJ. R AJ is the resistance of length of AJ of the wire. Now let small r be the resistance per unit length of the potentiometer wire, and length AJ is equals to L. So R AJ will be equals to small r into L. So in substituting the value, we will get epsilon is equals to I R into L. So this is how we can find out the value of EMF of a cell by substituting the value of current, specific resistance and length. Next is comparison of the EMFs of two cells. So for comparing the EMF of two cells, we have this diagram. So this is how we'll do this connections. So this is the primary circuit. So between these 2 points A and B, you can see a cell, standard cell, ammeter, a key and a rheostat are connected between points A and B. Now at point A, we have to compare the EMFs of two cells. We are having these two cells whose EMF we have to compare. So this is cell 1 having potential epsilon 1, this is epsilon 2. Okay, so the positive terminal of cell 1 and cell 2, these both are connected to point A, and the negative terminal of both the cells are connected to a two-way key. Okay, This is K2. Okay, now this is point M and this is point N. Okay. And this K2 end is connected to a galvanometer. This galvanometer is further connected to a resistance box, and this resistance box is connected to a jockey which can slide over these wires. So this is the basic circuit diagram for the comparison of EMF of two cells. Now, so the working, when we close key K1 and allow the suitable current to flow in the potentiometer wire with the help of rheostat. Rheostat helps in controlling the current. So we include this cell 1 in the circuit by inserting a key plug-in key in the gap M and C, okay, of K2, right? So this cell is introduced in the circuit. Now we'll adjust the resistance of resistance box to ensure that large current does not. So we'll increase the resistance of the resistance box so that the large current does not flow through this galvanometer, right? Now we'll start sliding the jockey over the potentiometer wire till the null point or a balance point is obtained. Suppose this null point is obtained at J1, right? So this length AJ1, this till here, AJ1 will be equals to L1. Okay. Now the voltage drop across the length AJ1 of the wire will be equal to the potential epsilon 1. So it is the voltage drop across the length AJ1 of the wire is epsilon 1, so it will be proportional to L1. Now when we will take out the plug from the gap between M and C and keeping the current I constant, cell E2 is included in the circuit by closing the gap NC of the key K2. So what we will get, we will again get a null point in the similar way for this second cell, and it will be at point J2 such that PJ2 is equals to L2. Now comparing these two equations, epsilon 1 upon epsilon 2 is equals to L1 upon L2. This is how we can find out, we can compare the EMFs of two cells. Next application is to determine the internal resistance of a cell. So this is the circuit diagram for finding out the internal resistance of a cell. So in this connect a standard battery E along with an ammeter, a key K1 and a rheostat across the ends A and B. Okay. Of the potentiometer wire. The positive terminal of the cell whose internal resistance is to be determined is connected to end A. This is the cell whose internal resistance is to be determined is connected to A. The negative terminal of the cell is connected to a jockey through a galvanometer and a resistance box RB. This is a jockey. Okay. Then a resistance box S is connected in parallel to the cell through key K2. Suitable resistance is introduced in RB to restrict the deflection within the scale of the galvanometer. So This is how the circuit is made. Now the working. So for working of potentiometer to find the internal resistance of a cell, we close key K1 or insert the plug in this key and allow a suitable current I in the potentiometer wire. Now we'll slide the jockey over the potentiometer wire till a null point J1 is obtained, and we'll find out this length AJ1 is equals to L1. So the EMF of the cell will be equal to the potential drop across the length AJ1. Okay. So we write it as EMF is equals to KL1. Now we'll close the key K2 and introduce the certain resistance S in the resistance box capital S. This is small s, this is shunt resistance, and we have named resistance box as capital S. And again the jockey is slided over this length of the wire and a new position of null point is obtained. Suppose it occurs at J2 such that AJ2 is equals to L2. So the terminal potential difference of cell will be equal to potential drop across the length AJ2. So we can write V is equals to K into L2. So from equations 1 and 2, dividing equation 1 by 2, we'll get epsilon upon V is equals to L1 upon L2. Now for a given cell, this EMF is equals to I into resistance plus internal resistance, and I1 is the current flowing through this S. So epsilon will be equals to I1S into I1 into small r. So I1 into S is what? It is terminal potential difference of this cell. So we are writing epsilon is equals to V plus I1 into R. Or we can write R is equals to epsilon minus V upon I1. But we know that current I1 is equal to V upon S. Right. So putting the value R equals to epsilon minus V upon V into S, or epsilon upon V minus 1 into S. Again we'll substitute the value of epsilon upon V from this equation. So L1 upon L2 minus 1 into S is equals to R, or R is equals to S into L1 minus L2 upon L2. So this is how we can find out the internal resistance of the cell. Thank you.